Hi everyone. My name is Indrajit, and I work as a senior software engineer in Informatica, and along with that, I am doing an internship with Start, and I actually lead the research team here. If anybody wants to do research work, can cooperate with me. And as my background, so I have done masters in data analytics planning, and after that, I have done few projects with basically on sentiment analysis using RNDS, statistical neural tensor network. And later, I joined Strat, and I found how we can, proceed with the research work and the new technologies, new algorithms that's coming into the market. We can actually always cope up with that. So we share our knowledge and we share what we learn, and also, we are basically focusing towards product development or producing research papers. So that's our goal. So along with that, now let's begin with today's session. So we will talk about QA systems. So I think anybody heard about QA, question answering system? So I think a lot of people are new here. So if you are aware of NLP techniques with natural language processing, what we do and what can be possible. So QA system is one of the oldest, but in the recent invention of deep learning, we have figured out a lot of possibilities, a lot of problems that can be solved with natural language processing using QA system. Okay. Now, with NLP, like if you heard about sentiment analysis, the basic of NLP that we start with, like hello world of NLP, you can say. So with that, we start with like say named entity recognition, and we have text summarization, right? So these are information retrieval. These are the primary goals we had for NLP. But in the recent world, we are trying to solve speech or when understanding text by humans, right? So what we actually send to computer, that's more important to be like understandable by them. And now the exploration is with different languages. We have so many languages over the world, and people are trying to solve language translation and even understanding of human languages, right? So basically, you are sending your message to the computer, and that should understand what you are asking. So that can be solved. That can solve many problems. Like not only asking a question, can be a reading comprehension, right? So you give a passage, and computer can tell you what is the summary, right? So this is not very new. I'll come to that history and what we have done so far, and what are the new things or algorithms that's been introduced. Okay. So this is one of the chatbot I was trying to test with. Okay, it's funny, and I wanted to take this example. So you see, I actually tried to talk with Eliza, a very basic Rogerian psychotherapist chatbot. It was invented in 1966. So you see the question that I asked. Hey buddy, this is Indrajit. I had a spell mistake. So he said, it is nice to be chatting with you. They said, I said, great, nice chatting with you too. Then he said, we are discussing you, not me. The system says, and I said, oh, I see. Then he said, okay, great, nice chatting with me too. Tell me more. I said, are you kidding me? I said, would you prefer if I were not kidding you? I said, yes. Then he said, I see, let's explore that a bit more. So, you can go on, you can continue to chat. And can you believe that it has been done in 1966? So, Eliza was one of the chatbot applications that has been invented at that time. And at that time, you might think deep learning and all these things were not there. And it was fairly good. It was very accurate in giving the answers. But it might not give you very complex queries answers with that. So the recent chatbot applications are different. The QA system is completely different. I'll come to that. So what happens? What is the QA system? So there is a huge misconception by a lot of people. They think that chatbots and QA systems are same or similar, but in reality they are not. They follow complete different approaches, methods, algorithms, and models. except the input and output which in text, right? So that's, and giving out a human language. So what is your system actually? So giving out a human language question and giving a proper answer for it. So like say sometimes a specific question is asked, and also sometimes a open-ended question can be asked. Right? Anything it can. So recent research works has given more efficient questions. So the questions that you ask, it can be anything. It is not that you think that the system can answer, right? It can be any kind of question that can be asked to the QA system, and it should be able to understand, formulate, and give you proper answer to that. Okay. Understood? Any questions? Okay. So what's the aim? So the aim is the QA system is to provide short and correct answer to the user, saving his or her navigation time. Right? That's the aim of this workshop, and also a QA system, that the recent QA system that's been invented. So what's the history of QA system? So I'll come to the types of QA systems that are mostly available okay, in the tech world. But if you see the history, 1977 Lunar is one of the QA system. It's a closed domain QA system that has been developed. I'll come to what is a closed domain and open domain. But before that, just get an example. Like Lunar was developed by NASA, and they basically developed it like to answer questions about chemical analysis of the Apollo 11 moon rocks and system of natural language, trip planning and project management. So it used to answer about the chemical formations of moon, and so there are multiple queries. I will come to that. What queries we used to ask to this Lunar. And TRIPSIS was another formation in 1998. The system that was developed as context for a research project. I mean, it was basically a research-oriented QA system, and it's to understand continuous speech understanding. That has been developed in 1998, and the overall system of which it was part was called Hear What I Mean. Okay, so HWIM. These are just examples. I mean, just to know that these QA systems are not new. It's almost 60 years that people are working on this, scientists are inventing new things. But I'll come to when the deep learning came and how that changed the complete idea of QA system. Okay, so then there was an example of Wolfie and QA, and then 1998, and decades later of 1978. So 2 decades later, that Wolfie was being developed, and then there was.
This is based on what do you call it? The technology that is rule-based. This is all rules-based.
Correct. There are different types of systems. So there some are ensemble, some are rule-based, some are probably web-based. Okay.
The previous ones, the older ones were not only rule-based.
Not only rule-based. Lunar was a rule-based system. Lunar was completely rule-based. I mean, you have a keyword. If the keyword matches, it will give you answer, right? So I did not explore much in depth the architecture. There are so many, but I have few slides on them. Yeah, I'll come to that. So open domains is a QA system. I have a track QA evaluation. That was 1999 and 2000, 2001. They have so many versions being published there. So today's workshop, I will be mostly talking about open domain QA system, and even the code is developed based on open domain QA system. Okay, so come to the Lunar. Okay, an example of the request understood by the system in that time. So they have developed, and it used to answer these. If you see here, it says the questions you see. Give me all lunar samples with magnetite. How complex the question is. It needs to know where the magnetite is, okay, and the lunar system. So it needs to read, and it has to basically calculate and then find the answer. It's not just reading from some comprehensive text. In which samples has apatite been identified? This is probably a simple question, but what is the specific activity of 8126 in soil? These are very complex questions that used to answer by Lunar, but these are rule-based. Okay, so rule-based means if I have, let's say, for example, A126 in soil, so wherever A1 toolsys has been described or mentioned, it will pick only those sentences and form an answer, right? So this complete system was developed based on rule. If you wanted to explore about lunar, there are so many research paper books in 1970s around, and they have so many rules, and they have developed the rules. They have books how the rules can be developed, but not necessary. Now we have deep learning, so we will come to that. I mean, already a lot of things that have been, invented in the recent times with natural language processing. So earlier time there was a challenge. The foundation of a QA system is its knowledge base. Okay, everything is dependent on knowledge base. If it doesn't have knowledge, it will not be able to answer anything. Given the current state of the art, a knowledge base can be broad or deep, both broad or deep, but not both. Okay? It cannot be both. Google's knowledge graph optimizes for width and well domain-specific knowledge bases like Google's consumer product ontology optimize for depth. So one side is the knowledge base, another side is the depth of the questions and the answers that you get. Right. So a complex question can have very in-depth answers. Right. So you can go in that direction, or you can have a huge knowledge base and it can answer whatever you ask. So this is a trade-off, a very critical trade-off in designing of QA system, where decisions are like emphasized breadth or depth, what to be emphasized. So this is always a very challenging thing with the QA system.
Sorry, asking a very basic question. What is ontology?
So
is the science of giving performance.
So it's a language specific question. So how do we find product ontology, like any kind of mentions of a particular product in a context based phrase. Okay, so that's where the ontology comes from. Okay, so going forward, so QA systems approaches. There are primarily three approaches that we follow with QA system. One is question classification, other is information retrieval, and then is answer extraction. So we find out the questions, we classify the questions first, then we apply information retrieval on top of that, and then we get the answers extracted. Any questions? Anybody knows about what is information retrieval?
From where the information is retrieved?
Basically, reading comprehension means you need that information. You
Correct.
read through that, and then after that you come to this.
Correct. So information retrieval is.
From where it will take?
So what do you think about information retrieval?
Entity.
No. Information retrieval is a concept.
No, it's before retrieval, that information should be there, right?
In Wikipedia, in your knowledge
Okay,
base,
yeah.
in your database, or it can be anywhere. It can be a document that is fed to the system,
Oh,
right?
No, but first you have to have
All values.
the text, and then you process the text to get the information, and then start this. Because word embedding and all that, is it part of this or is it before this?
So this is just a simple diagram. You do a lot of things in.
No, but this is before the data processing or after this?
This is very high level. Okay, so data processing, everything is done here,
Here, that's what I want.
right?
Then it is.
So information retrieval, if you think, let's say start with TF, IDF, CBOW, BOW, and then we have lexicalization on finding, lemmatization, stemming. All these things are information retrieval systems thing. Web crawling, whatever you call. So a Google search engine is an information retrieval based system. Okay.
So this word embedding words and all that, it will be part of the information retrieval.
Yeah, of course. So I mean, if you see as a diagram, I mean, and high level, right? No need to think about that. I mean, I will come to that, and those are very in depth. I have everything.
No, but that's what I mean. It is part of this.
Yes. So I mean, these are the primary approaches we do. Okay. So answer extraction is that we find based on the systems that we build. So a complete module is here. Let's say. Okay. So question classification is one of the challenging tasks we had with the systems earlier. Now,
how is it different from chatbot? It's also the same. You'll be asking a question and information retrieval, and depending on that, we will get the answer.
correct. So in chatbot, we have a specific question, right? So we ask, let's say, how can I find pizza, or how can I find where the Domino's shops are there? Let's say. So it gives you locations, right? These are the chatbots are very limited. They are not like, they will not tell you who is Obama's wife, how Obama is related to his wife, and whether Obama goes to this place every day. Chatbot will not be able to answer those complex things.
You're saying this will have a dynamic answer.
Yeah, of course. I mean, I'll come to that. There are so many things that you can do with QS systems. QS systems are, not reading comprehension. QS systems are not chatbots. QS systems are not just, giving you an Wikipedia answer. So can you tell Google search engine is a chatbot? Why? It is also giving you answers, right?
So chatbots are specifically trained in that domain.
Exactly. So that's the thing, right?
Is Alexa not a chatbot?
Sorry?
People say Alexa or Siri is a chatbot. They are not chatbots.
That is also, you can say, a small QA system. It's a QA system. But there are, there is no very much difference. But chatbots are basically conceptually different than QA systems. What it does and how the architecture is built is really different, right? So you cannot. That's what I'm giving you an example. If you say Google search engine cannot be a chatbot or cannot be an Alexa, right? Google also gives you answers.
Not only the answers, it gives the references.
It gives the references. So what it does in turn, it lists, it extracts the documents from the corpus, and it finds the rank of the documents or the highest rank based on the search query, and it gives you the highest ranked document, right? So that's what you get as an answer when you search. So that's the information retrieval is now in between these. What you do is completely on your model that you have built. Nowadays, Google search engine also uses deep learning, so there is no question on that. But these systems are there for a long time, and before chatbot and all this. So
It's very basic. It's even before the information retrieval, right? Question classification. Question classification, I'm assuming that you're trying to output a class.
what, why, how? What kind of, is it a what question? Is it a who question? Is it a how question? So you do a classification of the type of question that you are asking. How to go to Mumbai? Let's say. How to book a flight? Where to go? Right? Who is Obama? So type of questions. Question classification is that. To classify the type of question user is asking.
It will be a probabilistic model.
Yeah, of course. We'll come to that how we do that. Okay.
So the second question on that is, like, the scope of information retrieval. You said a lot of the pre-processing that we do. We do information retrieval. But in question classification also, because the data is semantic in nature, textual in nature. Won't there be similar pre-processing being done in the question classification stage also?
You can do that.
Because if you get data in that form, to output a probabilistic model based on max or whatever it is, you will need to, process the data, you need to tokenize it or may tell it or advertise it, depending on how you want to approach a model. So, won't it already be done here, and then won't that pre-processing then automatically work in second?
See, there could be 1,000 different architectures. The one you are talking about is one approach. There is already people have discovered different types of architectures, and it will take probably another 1 month to discuss about all the architectures. But I have taken few architectures which are been done and they were performing good. And if you see the squad, just search squad. If you see the competitions, you see there are whole lot of competition winners and the architectures and the modules that have been on the top list. So if you go over, it is already 30 or 40 architectures. I mean, if you discuss, so they are all different. Probably ensemble or probably a combination of multiple things that you are talking about.
When you say architecture, what do you mean?
RNN, CNN, LSTM, BERT, ELMO, okay, attention,
So it is
co-attention,
something
self-attention.
grade or something which is eighth grade also. It could be either of them.
So that is again coming to neural networks. So basic neural networks, you can have pre-trained model or complete training model. So that's up to you. But I'll come to that. Those are like you are coming to the result directly. So there are architectures, there are results, everything. I mean, if you understand from the beginning, right? So these are like going forward, that where and what, how, what to use. Now, when you say squad the page, right? These many of competitions winners are there. I mean, who are in the top who actually acquired say 90% accuracy. So which one you will prefer? You go with the accuracy, right? So there is no matter what other architectures were there. It doesn't matter. And also we cannot invent architectures just by looking at them. So because there are algorithms that has been developed and that is getting ensembled with multiple algorithms, and then we form another architecture algorithm, right? So architecture means, I mean, the algorithms that we use. Okay.
Basically, the complete solution, which includes
A complete solution. So you get the input, you do something, get the output. I mean, as a yes. But in the black box, there could be so many things. It could be nowadays we have. If I discuss about deep learning algorithms, they start with normal RNN, CNN, LSTM, BERT, ELMO. Okay, Albert. Now Albert came into picture. Okay, then attention, self-attention, co-attention. Okay, so all are attention based. Now, if you don't understand attention, if you don't understand LSTM, if you don't understand encoder decoder, there is no point of telling about BERT, ELMO, and all these things, right? So there are so many things. I'll come to that, okay, one by one. But if you have any question, you can always ask. So next is type of QA system. So basically, we divide QA systems in by the type of model that we have. Based on that, we divide them in 4 categories: closed domain, open domain QA system, rule based, like you were saying, and web based. Google search engine is one of the example of web based. Rule based, Lunar, I have given you example that uses a kind of a rule or syntax in its algorithm forms. Open domain and closed domain, these two are, it can be an ensemble, it can be formed using only rule based, or nowadays machine learning and deep learning can be used for open domain and closed domain. So due to the time limit, I cannot discuss about all of them. So I'm going only with open domain QA system. But I'll tell you what is closed domain.
Can you give the example for each one? Short example.
I just not told, right? For web based,
Google. No. Closed domain is what? For an example, what?
I'll come to that.
Okay.
So it deals with particular domain or topic. Okay, it can be an easier task of asking questions and getting answers, because NLP systems are very good at finding specific topic questions, and retrieving and answers will be very easy. So closed domain can work out very fast when the questions are onto a specific node, so that it can retrieve the answer for the question that is being asked. Right? So you basically know that what kind of question I can ask. If the QA system is built for, let's say, chemical formations, you cannot ask who's Obama, right? So that completely clears it out. There is no way that system is going to answer you those.
So by this, for the particular domain or particular.
Yeah. So by the name,
Technology.
as it can go with the name.
Is the answer will come
Search.
from the
Search. Your search could be a QA system.
Search.
Yeah. Search algorithm. Google search is something. There are certain sites. So for example, Australia is a search. Okay. Only searches. For example, he says chemical. You search some chemical abstract. You search it. It will give you all everything in chemical. Okay.
No, you are asking for
So it can be a search engine just built for that particular thing.
site.
Yeah.
It can be search engine
So
also.
that can be closed. Closed is like it's not expanded. It is just focused on a particular thing.
Is it closed? Does it mean it's not open? It's not open domain?
No. So closed is basically based on the topics. I can have a topic of chemistry, physics, biology, or anything, right? I can have anything. I can have a whole classroom of 10th, 10th class, all the subjects, and I have only one subject. So close, right? I'm not going to chemistry, only physics. Okay. Simple. Now,
It's like having a set of documents and saying the answers will come only from that particular set, not from other.
yeah. So question asking for descriptive will be more effective than procedural ones. Even machine reading applications are also created in the media field. Example, Alzheimer's disease. So there are actually, so you go depth of that. So the purpose of
It's the difference between depth and width.
exactly.
This is basically.
So this is always a big trade-off. You cannot say that only closed systems are better or open systems are better, because open systems you are having width, but when you go depth, only you asking about all that. In the chemistry also, again, if you go there, if you
It's
ask
to do
about
with the
molecules.
terminology also. Terminology in chemistry would be very different from terminology in
Yeah, exactly.
history. So I think that's
Exactly.
where the whole emphasis would be. The training of the data would be for the specific terminology.
Exactly.
And then it goes into
Alexa skill is an example of closed domain system.
Can be
But Alexa answers everything.
No, Alexa answers
based on the
basic
app.
things. Yeah, which for example, if you want Alexa to answer on visa related questions, you have to upload that skill to Alexa.
Correct.
Else it won't.
Correct. So
You have to train it.
that's kind of
Exact skill.
Yeah.
that kind of a data and the skill that you are fitting in, that's kind of a small closed domain QA system, you can say, that you are feeding to
If
Alexa.
you
That is
want the work app, you have to feed that skill.
so it's like an ensemble of multiple closed domain systems. Okay, going forward, any questions? So open domain QA system, as the name relies, it tells that questions and answering can be an open-ended and can be nearly any kind of domain or topic. Thus, the QA system finds the answers out of the help with information retrieval, computational linguistics, and knowledge representation of data for finding those answers for the questions given. The QA system takes the natural language question as an input, then the group of keywords. Okay, so in Alexa, in chatbot or somewhere, you basically say hi, and then it said hi, hello, how are you doing? Instead of that, if your QA system is like hi, then it says hey, by the name, hi, hey Salim, how are you doing? So it recognizes, let's say, I mean, kind of thing you can do. I mean, there is no such limitations with this system. So the QA system takes the natural language question as the input, then the group of keywords. This system aims at returning an answer in response to users' questions. The reply is a short text rather than lengthy list of relevant documents. Okay. I mean, it can be again. It's up to you. You can form that kind of system. Also, it can give you.
Does the open domain system also involve semantics?
Definitely, it involves semantics. So,
questions here. We want to, if you click here, you'll see the yellow font is not clear. Okay, maybe it came in the previous slide. Okay, fine.
Yellow font.
Yeah, maybe.
Oh, okay. This
Okay,
one.
yeah.
So, okay, any questions with open domain QA systems? I'll go ahead. So, semantics and syntax. So these are, if you have learned language and how languages are formed, human languages, not machine languages. So there we have syntax, semantics, lexicalization or lexicography, and then we have ontology, and then we have morphology, and then we have morphosyntactic structure. So how morphosyntactic happens with formation of syntax and morphology, right? So what is morphology? So the functions of a word, of a sentence, right? How you find the functions in a word. So it can be like normally sentence has noun, verb, and object, right? So there is a syntax. That's called syntax. How semantic is, so how that means something. So when we get the meaning, that is where the semantic comes in. So without meaning, there is no way you can get the answer from a QA system, right? So there is definitely semantic is involved. Okay. Any questions? So a brief history of open domain QA system. So there was a system that has been developed in 1964. The first exploration of answering questions from an expository text based on matching dependency parts of a question and answer. Then we have an example of Murex, 1993, aim to answer questions over an online encyclopedia using information retrieval and shallow linguistic processing. So linguistic processing is, I mean, the things where I discuss syntax and semantics, okay, of writing a language or what it means. Then IBM's Jeopardy system, DeepQA. That I will talk about DeepQA and Dr. QA. So DeepQA brought attention to a version of the problem. It used ensemble of many methods. And then Dr. QA 2016. When in 2015 around, we have deep learning came into a very huge usage, and I think the natural language processing guys started using deep learning for processing natural languages. So in 2015 onwards, and after that, Dr. QA in 2016 came with this information retrieval followed by neural reading comprehension to bring deep learning to open domain QA. By the way, China actually had done a lot of things before we even understood what was QA system and what is deep learning and all these things. So they have in the school, they have developed a system which were able to fairly like 50% able to answer what reading comprehension actually means, a passage or the answers to that. Okay. I hope it's not boring. You guys are able to grasp it so far. Any questions? Okay. So next,
40 minutes left.
40 minutes left. Okay. So I don't know how much I will be able to cover, but I will try. So this is one of the system in 2003 that has been built. Okay. So as we were asking questions about architectures and what it is actually, how complex it is, just look at it. So, but I will make it simple. Okay. So if you see the question processing, and what is that document processing, IR, okay, and then answers, okay. So as I see the over slide, if you see here, question classification, information retrieval, answer extraction, right? So that's the same architecture followed in 2003, and they have developed a system like this, which used to give factoid answers, okay, list of answers and definition answers. I mean, this is not very important, but just wanted to, I took this to understand or, make you guys understand that what it meant actually with the document processing, question and classification and all this. So what it does, it gets the question phrase, it finds the semantic information or transformation, it does the recognition of expected answer type, and then it does a keyword extraction from the list of questions or factoid of questions that is fed to the system. Okay, it can be from web or it can be database, it can be any kind of system that gives the information. Then we do named entity recognition, and then actually it goes to question processing, and then it does question parse, pattern matching, keyword extraction. So it extracts all the keywords needed to identify that question, right? Why, who, what, and type of questions that is going to be. So once it is done, then it does the document processing. So one side you are doing question finding and classification, on other side you are doing document processing, and then you are doing answer extraction. And it's fairly complex and very resource consuming system that was, but it used to be good. Actually, it used to answer fairly predict the answers to the questions that has been asked to the system. Okay, so I'll go forward. Any questions?
This particular system, which is old, have they upgraded to some other system which can do the same work?
I'm not sure what this guy has done. I did
No,
not.
not about that. This particular concept of this question and answering all these questions.
So This is
Have they
only
upgraded the
10% of my slide. I'll come to multiple systems. This is one of the system with the recent systems and what algorithms has been done. Okay, I'll come to that. So as I'm talking about Dr. QA, right? Dr. QA has been done using information retrieval and basically reading comprehension. Okay, so that was fairly good in I think 2016 that has been developed using squad like web questions and wiki movies. They have extracted the document from Wikipedia. So like the question is how many of Warsaw's inhabitants spoke Polish in 1933, right? So this kind of question that has been asked, it retrieves the document, it processes the document, and it has almost this much of documents to be read and then give the answers. So it was fairly good. I mean, it was performing well, but it used to give multiple set of passages or answers to that. It's not a very like say when did Genghis Khan attacked India or China, right? So the answer should be one line or one particular two words, right? 1991 or did not attack, something like this, right? But this used to give like this. So this was in 2016. So we'll see the new systems how they have developed, okay, in credit level. So recent works, machine reading for question answering (MRQA). So this is just a form, I mean, abbreviation, has become an important tested for evaluating a test bed for evaluating how well computer systems understand human language, as well as a crucial technology for industry applications such as search engines and dialogue systems. Right. So the research community has recently created. You see, these are, I mean, in recent world you will be able to find these things. So created a multitude of large-scale data sets over text sources such as Wikipedia, WikiReading, Squad, WikiHop, newses, and I mean other articles like CNN Daily Mail. I mean somebody have heard about maybe CNN Daily Mail. A news QA, race, fictional stories like MC Test, CBT, narrative. If you want to know about, I'll say Google about it. I cannot write everyone. I mean about everything. And general web sources, MS Marco, Trivia QA, Search QA. These are kind of new things that community has found with the recent, involvement of deep learning and text processing techniques in natural language processing. So now I'll come to the today's workshop that we are basically working with Squad dataset, right? So any questions? So I'll now from this I'll go a little slower because these are like little in depth. Okay. So as the name, right? Stanford question answering. I mean, Stanford has developed this with a crowd source, basically with the crowd workers. So they have chosen few. I mean, a lot of people to develop this data set. Okay, they ask them to read the passages and form the answers, form the questions, ask typical questions, or ask very critical, very complex questions, and those questions are formed as a data set. So the questions are not even using any keyword from the passage. So a passage is given, and there are like 10 different people. They have given 5 questions. They have given a task of forming questions, like 5 questions, without using those keywords to ask to based on the passage, whatever it is. So those are the questions that has been given in a Squad dataset. Okay. So this is an open data for QA system, and we will look into it later. And the Korean version is for QA. Brief description. Basically, this has been worked by I forgot the name, Danny Chen or some a Stanford professor. She actually has been contributed a lot with Christopher T. Manning for this data set development. So in 1.0 version, 1.0, the answer was unconditional in the passage, and the system only had to select candidates and then rank. So we did not have to check whether the span was the answer. So you get it? What is span? So it is saying that you made something with no answers. Okay. I mean, in 1.0 version, they actually had like the fun that there is no answer. Only you have questions that been formed. So actually, I'll discuss about that on the next slide. So but actually, squad data set is meant with different types of questions that it can pick, and it can give you a very specific one word answer. So squad yields only an unconditional span-based answer. The question is constructed for unconditional passages, and there is a title, multi-fact, or sentence interval. So still, it is called a well-targeted, well-structured, clean data set. Recently, Squad 2.0 has been released, which includes unanswerable questions. Right? So we'll see how it works. Go demo. So I just took an example. One defining characteristics of Squad is that the answers to all the questions are segments of text or spans in the passage. These can be single or multiple words and are not limited to entities and spans. So if you see this, so just a small passage. It talks about how did some suspect that Polo learned about China instead of by actually visiting it. So answer is through contact with Persian traders. So actually, if you read about this, it talks about Marco Polo and it's his travel of China and what he visited, and then says. If I read one sentence, say some argue over the accuracy of Marco Polo's accounts due to the lack of mentioning the Great Wall of China, tea houses, which would have been a prominent sight since Europeans had yet to adopt a tea culture, as well the practice of foot binding by the women in capital of Great Khan. Some suggest that Marco Polo acquired much of his knowledge through contact with Persian traders. Now the question is, how did some suspect that Polo learned about China instead of by actually visiting it? So the answer is through contact with Persian traders. So span is, answers are spans in this passage, right? So that's just to know what is span. So basically the answers, but we can have different answers also. Different the questions are very very complex. I mean, it is not something straightforward that when Polo appeared in China or went to Europe or what he visited, right? Any questions? So spend around see here spends around 4 minutes on the following paragraph to ask 5 questions. So I found it like, but it's not needed actually. I mean, just to understand that. And if you can't ask 5 questions, ask 4 or 3 words. But do your best to ask 5. So select the answer from the paragraph by clicking on select answer. So this is in the Squad dataset. You can just try it out. When ask any complex question, it will give you the answers. When asking questions, avoid using same words or phrases as in the paragraph. Also, you are encouraged to pose hard questions. So you can just test it. The system. Now we use this data set for our primary for our model today for building a QA system. Now, okay, before I go forward, Stanford attention reader. Vivek, I would like to explain things on board, so I'll go forward from this. So I'll pause the recording, or shall I use marker and go to the? That would be kind of time taking. Yeah, I cannot write it.
So if you're speaking, you can continue the recording. As long as you're speaking, they can still hear it. See, I'll use the marker, whatever you're writing there.
Yeah. So the people, this is for the people who are very new to the algorithms, neural network, and how how the attention and RNN and these things work. So I'll just give you overview, and that's very important to understand, because with the next slides you would not be able to get what it is talking about, right? So these are fairly complex if you do not know. If you know, it is very simple. So I'll just tell quickly about what how RNN and everything is formed. So from the basics, as an example. So given a sentence, I am okay.
No, they don't have power.
The cloud is, I think this is,
You can use black marker.
that's better, yeah.
Black or red.
So I'll take one sentence.
You should not do that.
Is it clear?
Yeah.
So the cloud is in the sky. Right? Where is the cloud? In the sky. It's very easy to answer. Now, what we do with NLP, we try to predict or we can find the probability of the most or the given answer. So what would be the cloud is in the sky, or so where the cloud is, so the probability of the answers would be okay, so I was coming to that. Say y is a function of x. So I have an input of x. What is the input? Input is these words. Okay. What would be the y? Sky. Right. So I need to find a y that will give me the answer. So I can apply argmax on these. Okay. So a word at time t and a word at time t minus 1. So a word cloud and t minus 1 the previous word, right? So I need to predict yt minus 1.
You predict white T plus 1. So in future, what do you ask?
So I will be applying the previous word. I will get the previous word to get the output. So y hat would be the answer. T plus 1 would be y hat.
Okay.
Right? That's the answer. We'll find. I'll not make it very complex. Now this is a function.
There has to be one more argument. You cannot have white hat is equals to white T.
So we can have with this. We can have y 1. Okay. So we apply argmax. It can be softmax. Anybody knows about softmax? Yeah. So we can apply softmax. So softmax e to the power x by 1 minus e to the power exponential. Okay. Even from the graph. I mean, I'm not going that because it's not possible to cover it. Now, I'll come to how encoder and decoder architecture is built using this. So, normally with what we do with RNN, we feed some words. We try to predict what would be the next word. So we will through the hidden state, right? So normally, what happens to vanilla RNN network, recurrent neural network, right? If you know about neural network, it's good. I cannot with neural network. Probably you can. These are the prerequisites, so you can go back and back to a lot of things. Okay. So what are these? X1, X2, X3, 4. Okay. So I have these inputs, right? And that goes to the network. And I get a HT or let's say hidden state. And finally, I get a output. Right? This is normal. This is normal RNN.
Okay, RNN.
Okay. Input, hidden state, and output. So normally, what we do in RNN is whatever we feed in, let's say I is a word, right? In the same structure, we feed into the next layer, right? we feed into the next layer, and then it goes to the, from here it goes to the next layer, right? That's what we do. Now, in this way, when I have I, or say the cloud is in the sky, so it should tell me the next word, right? So the how we'll find the predicted word? So in RNN, we feed the previous word t minus 1, yt minus 1, and we get the next or predicted output. So normally RNN works like that. There is no difference. So if you see here, if I add now a encoder network which gives me the previous word. So in what we do in on normal RNN, we feed the to the next layer. But what is the, let's say it is S0, S0 state, S1 state, S2 state. So how does it know what to feed at S0? We randomly give something, right? Da or something, right? I mean, just example of words. It can be a document or it can be multiple documents. Now, what we are feeding, that is like a random word that we are choosing to feed into the network. That's a S0 state, right? And correct me if I am wrong.
So you feed the word, the sentence in the.
We feed the word. So at the beginning, at S0 state, we feed something, right? The word, the da.
Yeah, in order.
So if I have any other network, it is coming. The output is coming from the previous hidden state.
Yes.
What I mean is that is coming from even the previous hidden state. Now, what if I wanted to not feed only the thing that is coming from previous state, but the words which are having more or high probability. Okay. So I have these words, right? So let's say these having probability P1, P2. This one has high probability. Okay. I want to feed this, not the previous word that is coming from the hidden state. Basically, the previous so S0, S1 is defined that I will get S0's hidden state output, right? In RNN, normally that's what we do, right? Now I don't want that. I want the words which have highest probability. I apply softmax. I get the words. Let's say this is having 0.5. Once I normalize the values, I get 0.7. I get 0.1. I get 0.4. So highest probability is 0.7. I'll take that. Okay. So next, I have similar structure, which is a decoder. This is an encoder. Similar structure, other side you put it. That is a decoder. What I will feed in? I can feed in the hidden state of the previous layer, which is normal RNN. But if I feed in applying softmax, the highest probability word to the next word, next layer, what is that? That is attention. Right? That is attention. So the word with highest probability I am feeding into the next layer. That is in the decoder layer. Decoder layer is the same structure. Any questions?
So you won't feed the last one to the decoder.
I won't feed the last word.
You will feed the highest.
probability.
I'll feed the highest probability word. That's after applying the softmax. Whatever word has the highest probability, that will go to the next predicted word.
I thought attention was a co-linearity matrix between decoder and encoder output.
It is a similarity matrix that
Yes.
has been formed, but it is not that matrix only. But we get the value. Now you can form a matrix with these attentions, which is called like co-attention.
Indrajit, suppose you don't have 0.7. Say you have 0.5 at both sides. And which word, what will it take?
That is again mathematics, right? So if the probability is similar,
It will pick one of them.
It will pick one of them.
You can do floor or like.
Yeah,
Mathematics.
that's a mathematical functioning. So it is not nothing to do with again network.
So,
Right?
I will get the probability. I will get the probability.
The softmax?
No. Like with respect to this output of
I didn't get it.
This is how will you arrive at 0.5?
encoder output also is needed for the probability calculation, or simply encoder output.
Encoder output is what?
Hidden value.
So which hidden factor? We are getting the value or the weight of the words which has highest probability. That we are feeding to the decoder, right? What your question was, how do we find the probability? We apply softmax on the vectors that we get for those words.
See, this is attention, right? It is creating a multiple.
Exactly. That's the attention. So you get the highest probability word on the top. So that's what you feed into the next layer, the decoder layer.
What's the encoder and the decoder? What are those?
So okay, you understood this. What is this? RNN. Now, normally there is, if you don't look at these networks and everything, it's a simple equation. Y is equal to fx. F bit. So y is equal to fx. F I replace RNN. F I will replace with LSTM. F I will replace with GRU. F I will replace with BERT. F I will replace with Albert. Anything, right? Now, if I form the architecture with encoder, which encodes and gives me the hidden states of the previous layer and tells me what would be the next output, that I will feed into the other layer of same. You are copying. You are having a copy of the architecture in the next layer. The output of the previous layer you are feeding into the next. That's what encoder and decoder is.
Decoder is the next layer. I mean, next.
So, what you are decoding? The cloud is in the sky, right? What is the decoded output? Sky. Right?
It's like English to French
It
translator.
can be English to French.
So English network is called the encoder. The French output network is called the decoder.
All those words, the probability was the highest for sky, so therefore it chose sky. Therefore,
That is attention. Our question was that what is encoder and decoder? Okay.
but if you go by this, what you explained the beginning, is that what sky does? You just said that you are inputting this and the output is sky. Is that what?
So your
We said y is equal to fx.
your
Is sky the result?
Your output or your intention could be anything that what you want to achieve, right? So that's completely up to you.
No, let's say John went to the market, but he did not buy anything. So there is an attention between the word John and the word he. Okay, right?
Yeah.
Something like that. So John went to the market, but he did.
You have a vector 0 where you put that. Those lines.
These are neurons, RNN neurons.
Yeah, those are RNN neurons. Now that RNN neurons, you have those lines, right, which you put.
It is building attention between encoder and decoder.
How are you going to assign weights to that attention? Because only when you multiply your vectors with the attention with the words, the probabilistic words, will you get the highest attention. Otherwise, when you do not have the proper probabilistic value to that, or this is the right word, how will you get that attention? That is the whole question.
See,
So
it learns.
the thing is, I got your question. The thing is, how do you get the probability that you need to know first? Your question is, how do you know which?
How do I assign weights to that? Those.
No, it learns the weights. It builds the attention vector.
So in neural network, we always assign weights. You know that, right?
Okay.
By training on lots of samples, it learns the relative importance.
That's it. It's very basic. MX plus C.
Okay.
Okay. I don't have anything to explain apart from this. Okay, and now I was coming to something. I had another question somebody asked. Because I want to clear this, then I'll go to the next slide. Because they are like having thousands of, let's say, attention layers. And then co-attention, self-attention, and so many things.
No, I am thinking, let's say English sentence, I drink milk. Corresponding French has the word douche. Let's call it the word douche, which means milk. I don't know which is the French word. So what it will find, milk and douche always co-occur in the training data set. So it starts building attention between the word milk and the word douche, which it thinks they always co-occur in the training data set thousands of times. That means they are correlated. It finds the attention between them. Okay, I am thinking roughly like that.
But co-attention is different.
Okay, I mean there are variants of this.
Yeah,
there are.
types of attention. Co-attention is different.
Okay.
I mean, as a normal thing, you get from one state, the hidden state, and the value of to the next layer, right? Next state that you fill in. Instead of that, you are applying to your question. So it can be an image also. Okay, I fill in. I have a softmax or state, and then I get the output. So a image, someone is throwing stones. Okay, so I want to have a question who is throwing stones, or it might be the name or what is being thrown from the image, right? I have an encoder network. Whatever output I get, I put it to the decoder, right? Now, this is the image. It can be a Hindi word, something you cannot write Hindi, and so that translated to let's say India, right? It can be India. उसको मैंने हिंदी में लिख दिया है. Yeah, I don't know how to write, but in India, ठीक है? Right, so मैंने यहाँ पे हिंदी में लिखा. I want to answer. So how do we do that? I mean, I know how to write Bengali, so that's the thing. Okay. So any language, okay? It can be any language or any word to any other word. I am going from that. So whatever input that you give, you want the output based on this, and everything softmax and the function, everything is there is no difference. There is no difference. Whatever input you give, it will give you the output. There is no change in the architecture. I just wanted to make sure.
Yeah, one question. If it's Indian, it's doing auto encoder, right? If it's single word, there is no need of attention, right?
If it is a single word, generally we don't go with single word.
Okay. The other multiple sentence, out of that, we get to take attention.
So just to understand, paraphrase what I understood, first have these input layers for LSTM from one LSTM to the next and so on. So all of that together they form your encoder. And then whatever.
So encoder will give you an output. What is that? The highest probability word. This will be the
depending on what you're using in terms of activity.
So that's no matter whatever input I have. So I have a so how it goes, there is a data set. There is some certain parameters. Okay. It can be weight, it can be any of your functions that you feed in, and then you have a encoder. You have a decoder. So these things will vary based on what kind of neural model you are using. It can be RNN, STM, or anything, right? And then you have an algorithm. That algorithm may change based on what kind of output you want after that, right? After you pass through encoder and decoder, you want to change anything. And then your final loss. Okay, there will be a loss function, right? The loss function will be minus t equal to 1 to t minus log of theta. I'm not writing that summary function. It is right. It depends on what error function. So this is then completely with any model will have this. It's a basic architecture. Now I will come to the slide. So attention is still not here.
But the same architecture, how we can use for different applications?
I'll quickly take that your question later. Okay. First, latency should be clear because I see people are still not aware of what is latency. So, okay. So it is a very simple thing. I believe there is no there should be any confusion. Normally, if you understand neural network, what we do in neural network? Tell me what we do.
So you have an input layer, or you have to basically start with an input, then you have a series of hidden layers, and depending on how much you want to find in your network, you have the hidden layers. Then you have an output layer, wherein you have a loss function and so on. And then you start to propagate a neural network.
So those things are I'll come to that with adding more things. Now, normally that is a normal neural network. If you say RNN, recurrent neural network. Recurrent means you are feeding in the previous state to the next state, then next state, and then next state, and then you get out, right? So what is that you are feeding in? So the first state, whatever state I have, whatever output I get, I feed in.
So H theta you're feeding into the next.
Yeah, so you get an output, right? So normally any RNN looks like this. X1 is the input. I apply softmax or whatever, I get the output, right? If it is I have I, let's say these one will go to the next. This is S0, S1, S2 like this, right? So what is going? I. What I am saying is, when we go for
the output for S0 will become the input for S1.
Yeah, that's what it happens, right? Now, I am right. I am trying to explain it again. Please understand it correctly. If you don't get it, this time you should get it. I'm trying my best. Now, so what we do is we go to this and we put it to the next layer, right? And next layer, and so on.
So you're basically training on past data. Whichever past data output is there, you are adding it to the next data.
Okay. Whatever I have told so far, to understand that, you need to remember what I have told before.
Yes. The past experience plus the next experience.
That's how human works.
Yes.
Same to the network.
The sequential intelligence. The next word depends on previous word, which depends on previous word. So sequential intelligence is being preserved.
Now, when I tell that I need to find some answer, and I need to know which is the answer, like I want to give attention to that word. So attention is basically, let's say, Vivek is the co-founder of SalesTag. So I have to give attention to Vivek, right? Rest of the things are not related. I mean, it only comes if Vivek is there. Co-founder and everything is
not important.
So how do I do that? How do I do that? I need to find some way, right? So with mathematics, that is softmax. The softmax is e to the power x by 1 minus e to the power minus x. Now don't ask me how that is coming from, because that's a derivative. If you do ddx of e to the power x, you will get the answer, right? So exponential. So now, once we apply softmax, we get a value. So we can apply softmax in all the words. Vivek, co-founder, SalesTag. Right? Now we get a probability value. So whichever has probability, high probability value, that we will pass into the decoder. So now that probability value, the hidden states value, that is what the attention is. So attention is nothing but the highest probability of the words. Any questions?
So basically, as a softmax input, you're giving the complete sentence, and from the sentence, you are saying, okay, this has got the highest attention for the first. Vivek has the highest attention. Then you have Comax, whatever.
So I will pass to the decoder only Vivek.
The most significant word.
The most significant word is
Also
the
get the
decoder.
classifier softmax or whatever you're using the application. Those set of outputs for each of these S0, S1, S2, let's say SD or whatever. They form a set of what are the
How was it determined which is the most?
Is that right?
Sorry,
No.
just jumping in between the words.
It needs RNN knowledge.
So
It needs
I
RNN
have
knowledge. Unless we have studied RNN, it's difficult.
Okay. You got this one?
It's a very big
what
topic.
It will give me the attention. Now I have the architecture same like that. Okay, same architecture. Copy of that. What it is
This
giving
very
me?
close to the translation.
Vivek will pass to the what I will pass here. Whatever word I had. Vivek I had. But I am not passing anything to the other layer. What I am passing? I am passing the output of the previous layer. So this is the same layer, same kind of structure. I will call it decoder. I will call it encoder. Okay. So Vivek is going there to the decoder.
after this entire process is done.
Yeah. Okay. Any questions?
Okay, BERT is a component of self-drag, then we'll only get the BERT and we are passing the BERT.
Passing through the decoder.
Okay.
If we have applied,
So only one, so it will be continuous, right? It will be not only one word will only go.
it is a sentence, the document is a corpus.
Okay, okay.
Just an example with one single word. It can be image, it can be speech, it can be anything, it can be a video.
But one BERT is a component, then we will be passing another sentence also, right?
Yeah, right. But now, any questions? This is encoder decoder is clear.
What is the output of that? The input in BERT. What is the output?
The trade get output, right? Clear. The question is, so my question will be, who is the founder of Self-Stack?
Okay, okay.
So Vivek.
Okay, okay. This for question answer.
No, I mean I told you that it can be an image. Who is throwing stone to in Kashmir to the soldiers, right? I mean, when I was trying to mention here what exactly we are trying to do, right? So finding the attention to see which is giving highest problem. Now, normally it is all the words. Normally, from encoder to decoder, everything goes. The vanilla RNA network, which is like a basic RNA network, that's what it goes. Okay, without encoder decoder also, and can be used. Now, then comes encoder decoder, then comes attention, then comes LST. Okay, long short term memory. I'm not going to that, but just a one line. In RNN, it remembers the previous state. But what if I have to remember more? Like, yeah, so LSTM is the solution to that. So RNN cannot remember. Like Vivek is co-founder of Self-Stack, Vivek is chief data scientist. It needs to remember two things, right? So I mean RNN can do, but it was not fairly good enough to solve that problem. So we had an LST. Then we have bidirectional LST, right? And then we have attention on top of that. Okay. So ultimately, the same thing, the architecture is same. Only we are adding something extra to that. Okay. This is end here. Yeah. Any question?
Can you output any kind of sentences using this?
What kind of sentences?
For example, how's the weather today?
Yeah, that's the purpose, right?
Yeah.
You solve any something, image, video, or any kind of input that you provide. Is trying to give you the output, or it will
That
give
sentence
you.
formation is done by this decoder.
What is sentence formation?
For example, we got the attention word as sunny. The weather today is sunny. That sentence formation will be done by the decoder.
What is your goal?
I want to output a sentence for the question, how's the weather today?
So normally a neural network tries to solve a problem where you try to convert a language, you try to feed in something, based on that you get the answer. The chatbots are also built in same. Your feeding is like some information that you give. Based on that you want the output. It will give you the output. It will give you the highest probability of the word, so you know what is the word that I have to focus in. So I get the word, I get the predicted word. So I as an output, you will get that word.
So I think just make it. So you asked a question, where is the cloud is in the sky. You asked the question, where is the cloud in the sky?
In the sky, so, or sky or whatever. Because sky is the word.
Okay, so in this, okay.
Not in the sky. Sky is the output. Okay. The problem can be any kind of thing. So if you need to actually, it is not something that you need to work on it. I mean, you need to work with multiple inputs or type of examples. Then you will be able to understand it. But for now, I am not covering that. Just for an example, that this is what it is. If you feed in, let's say, Hindi word, it will give you English word. How it does? Encoder, decoder, attention, and all these things. Now, I'll come to this Stanford Attentive Reader. Okay, so in 2016, Jane Bolton and Jen Fish, Western and Borders, they have developed this algorithm, Stanford Attention Reader. what it uses is it uses a LSTM, bidirectional LSTM. So it has a question hidden. Okay. So all these question, which team owns Super 50? That's the question I have given to the network. Okay. Based on this question, I will get the answer. Which team owns Super 50? Okay. So the passage is here, input. Passage is here, right? My question is, which team owns Super 50? So the system has to read the passage, process it, feed in the question, you get a similarity, score between them, and then you get the answer. So another concept comes here. What is similarity score? Cosine similarity. So you know about globe, right? So what we do in globe? Embedding. Yeah, word embedding. So you're talking about word embeddings. So we find the words which are closer, nearer in the vector space, right? So man, woman, queen, king, right? They are in the separate titles. So based on that, we find the words which are closer to certain things. So cosine similarity is, let's say, a document, means passage, and I have a question. So passage fits in and the question fits in. The match, the similarity, I mean, the closer match will give you the answer from the passage, right?
So this globe is actually not a data set itself.
No, globe is a word embedding.
But word embedding with a lot of
yeah, you can say it's a library that we use.
Library, right?
Yes.
More of a library.
It's a library.
Yeah.
Yeah, anything. Both are similar kind of.
So when you say library, it has contains all the
word embeddings.
different word embeddings.
Yes.
Synonyms, antonyms. everything.
Yes. Any questions? Do you want to take a break or after that?
I want to ask you two things. Now, you have the which, you have two sets that are walking. Look at that image.
Yeah.
Which one is getting directly into a lower level, and one is getting into upper
With
level.
RNN, if you see the architecture, it always passes from the previous state to the next state to the next state. Same thing. Okay?
Bidirectional.
It's a bidirectional. So that's why.
Why does it use bidirectional? That's for mine.
So what is bidirectional?
Go to right, right to left.
Yeah. Past to future, future to past. Bidirectional. Simple. Now, is there any other question here on this slide? I'll go move ahead with the next slide.
How do we train this model?
So, is there any difference in training normal RNN or LSTM than this network you feel, or if you know how to train an RNN model?
Yeah. But like in real time, we are giving the passage. Right? In real time, we are giving so it's just a.
Well, training also we have to pass the passages, right?
Yes.
Passage and questions.
Passage and question you need to pass. In the data set, like SWOT data set, we have the questions, we have the passages. I told you at the description of SWOT, what it is, right? It has a passage, it has a complex questions. So we pass the question, we pass the passage, and we get the answer. Any questions? Okay. I'll go ahead.
Go ahead.
So this is what it is. So who did Genghis Khan unite before he began conquering the rest of Eurasia? That's the question. Okay. And I'll come to the next slide where passage is there. So I apply a bidirectional LSTM. So it has a two bidirectional LSTMs. Based on that, I get the output. Okay. So this is the passage that we pass in. Okay. And that predicted start token, I'll have a attention applied. So attention is basically the softmax applied on the function, right? The question. So Qt, if you see, with a weight vector, right? Attention, please. So important topic. Yeah. So bidirectional LSTM. So we apply to bidirectional LSTM. On top of that, we have attention, and then we get the question feeding to the network. Based on that, we get the output, the answer. This passage is also fed into the network. So my data set has a question and a passage.
Answer.
Answer I will, okay, ready, I will get the answer, right? So you ask a very complex question, it should be able to answer. So if you see here, the red and the colorful things, right? So probably these are my softmax applied attention words. He came to power by uniting many of the nomadic tribes of Northeast Asia. After founding the Mongol Empire and being proclaimed Genghis Khan, he started the Mongol invasion that resulted in the conquest of most of Eurasia. Okay, so I have given attention to the words which are having highest probability, right? In that, I have two bidirectional LSTMs. Then I feed in the query, and we find the similarity between them, and based on that, I get the answer. So these are there are a lot of basics that you need to know to understand this. Like if you don't know cosine similarity, I mean, to picturize or visualize it. If you don't know it, it is tough. So document and question both goes parallel. So in a vector space, they have an angle. So the angle is closer, they are more similar. Okay, the angle is more, they are less similar. It's 0 to 1. The value is between 0 to 1. Okay, a document and a question have a dot product. Got it? Q into D, Q dot D divided by Q cross D. Cosine similarity. You get a score. Q dot D divided by mod of Q. Mod of D. Okay. And you can do root over also because to normalize.
Closer the values to 1 or 1 is that.
So these are, I mean, I would say if you don't get it, these are the basic mathematics. Explore that. Don't need to start from basic algebra. Learn cosine similarity. Learn normalizing vectors. So you will get to know. I mean, that will give you a purpose.
The whole document against a single question. Dot product.
Sorry.
Whole document against a single question.
Yeah. Whole document against a single question. Correct. So you get a how do you get a value? So you apply, let's say you can have Jaccard coefficient, you can have TF-IDF. You apply TF-IDF for a document, you get a score. You apply TF-IDF for a question, you get a score. Those two scores, you do dot product, you get a value. That's what the cosine similarity score will be. So that cosine similarity, the more, I mean the passages which are getting more score, only those will be my answers. The answers will be formed, and in that I'll give attention to the words which are having highest probability. Got it? Any questions?
Two levels basically.
Two levels. Any questions? I'll go forward.
You said two words. One is cosine similarity. Second one is what?
Jaccard coefficient. Okay. Jaccard coefficient.
Coefficient.
So this is one of the spot results in 1.1 version. It has been done in 2017. So if you see logistic regression, I mean the F1 score for these algorithms, there are so many algorithms. You are asking, right, what architecture I should be using. In 2017, they already have tested and did competition with this. So DRQA, BIDAF, DCN, if you see match LSTM and fine grained getting. So this is done by Garning Madam. So if you see the highest score is DRQA, Dr. QA. So that in 2017 got the score, and human performance is 91.2.
Can we benchmark from self-stat side? Can we be present on this kind of list?
It's possible.
Possible. Why not? Why not? But it will take time. We did not focus on efficient coding. We focused in presenting it as a workshop, right? So we can do that. Certainly we can do. Even me and Abdul were discussing yesterday night.
We should benchmark our own results.
Yeah, we can do that.
Publish a paper around it.
Definitely, we can do that.
The human government means what they are doing. What is human? These are better.
You are the human. You are telling me the answer. So I'll get the exact answer. When did Genghis Khan invaded, right? So you will be able to give me the answer, right? And system will give me the answer. So you are 91% accurate.
So then I could be more than that.
You can be 100% also. Yeah. Okay, so I mean, obviously systems cannot beat humans, but in future probably it can.
Human beings have got so much of pre-trained knowledge acquired in them over so much of time. Here you're talking about building a system at
So it reads a passage. It reads a given passage. Based on that, it only gives. It doesn't know so much of things. If a system is that much trained with so many data, it will become human. Anyways, not wasting time on that. So going ahead with itself, now Stanford Adaptive Reader Plus Plus. The one what we had with a bidirectional LSTM, two bidirectional LSTM on top of attention, and then we feed in question and the document. The same thing you multiply. Okay. Question is, when did Beyonce's P1, Q2, Q3 is the question. Beyonce's debut album, P1, P2, P3 passage. So these are the passages. These are the questions. Feed it in. I get the attention of the passages. I get the attention from the documents, from the questions. That I feed into another bidirectional LSTM, and I get a similarity score on top of that, and then I predict out. Any questions?
It's more and more complex.
No, but I think this is simpler now. As I explained, what is attention, what is RLM, how the architecture is. So there is nothing. I mean, it's fairly clear, I think. Any questions? If anybody has any doubts.
So what is the training objective?
So training objective is the loss function that we actually try to minimize the loss, right? So this is based on the paper. I mean, my training objective is not that, but based on the paper, they generally find out the loss, right? So minimizing the loss. So they find the loss between this the training models with the question and passage. So if you see the two loss functions that has been applied on both the networks.
Okay, this is basically you're trying to minimize the loss between the encoder and the decoder, right? This loss function.
So
yeah, because that's when you're trying to when data comes from an
so
encoder to a decoder.
any if I go back to the basic, any encoder decoder, I will find the loss.
Yes.
Right?
Yes.
I have multiple encoder decoder.
Yes.
And combination of the network. So I will have combination of loss functions, and finally I get a final loss. Right? That's what it is.
One second. Sorry.
So if you see here, with the neural models, the categorical feature classifier, those actually improved a lot in this Stanford attention reader. So that performs 79.4. Humans are still ahead, 91.2, and Google AI SOTA has 91.8. So in February 2016 and October 2018, this is from. So that's why Google is better. BERT and BERT LSTM is doing far better than any other algorithms. So what do these neural models do? If you compare with neural network with categorical feature classifier with the machine learning, right? So exact match easy. So if you see here, the exact match has 13% almost the accuracy, and paraphrasing has 21%. Partial has 19%, and multi-spent or hard error has this much of correctness you see.
These are different types of classifiers.
Neural network along with comparison between neural network and categorical feature classifier.
Okay.
Categorical feature classifier is machine learning,
Classic machine.
classic machine learning. Okay.
Okay.
And we should not forget classic machine learning also with deep neural network somewhere. So
Why
now,
R is very low?
which one?
For neural networks, R is low. For neural networks, R is quite
Yeah, I mean, that time it was not that well good, but I think nowadays the performance is far better. We have attention, self-attention, co-attention, so that got improved. I'll come back to it. So now, from those architectures, we move ahead to bidirectional attention flow for machine comprehension. If you see here, if you see this side, so I have an output layer. So it starts from here. Character embedded layer, glue or anything you apply. Word embedded layer, phrase embedded layer, attention flow layer, have modeling layer and output layer. Okay. No need to understand this too much. It's a complete paper actually. I just took this because whatever we have discussed before. So just to have an overview of the architectures that been formed in the recent ages, right? So
the character become where from the word we can process, and then from that we can add in the attention.
correct.
Then modeling added.
So modeling layer is the LSTM, bidirectional LSTM, multiple LSTM. So you pass it to that, right?
The context is what? The context of the.
So context is very important, right? So you only get the context when you know what it was talking in future or in the past. So based on that, you get the context.
Tense context.
Yes, tense context. So it's a language understanding on that basis that we get the context to query and query to context. Okay. So there are variants of any improvements improvements to the BIDF architecture over the years, but the central idea is the attention flow layer. Attention should flow both ways, from the context to the question and from question to the context. Next, similarity matrix with W of dimension 6D. So we have a similarity matrix that has been formed with the 6 dimension, with this architecture that we get. So context to question attention, which query words are most relevant to each context word, that we find out on this architecture. Okay, so these are more little add-ons on that side, but ultimately, why had equals to softmax of the function is the same. You just add on something. Okay, and people are getting sleep. So shall we stop even for some time break, because we can continue. I have few slides left after this. Probably another 5-6 slides.
You can finish that.
Huh? Shall I finish?
10, 15 minutes.
Now?
Yeah, 10,
Yeah, I can go fast.
10 minutes.
Okay, let me finish. Okay, so recent more advanced architecture. So most of the work in 2016, 17, and 18 employed progressively more complex architectures with a multitude of variants of attention. You see, so we basically use different types of attention, right? And those are in recent years with the neural network architecture. We only change the attentions. So if you see in the squad board 2.0 in 2019, last September updated, Google Albert. So BERT is the top algorithm that has been scored 90% and 91%. I'll come to that slide also. So
After BERT, there is Albert.
yeah. No, ALBER. So there is a DCM I talked about earlier, right? I just showed the leaderboard of DCM, which was actually fairly good, and that was also a good architecture. DCM 75.9 in 2017. Now they have updated a lot. And if you see the DCM architecture, it's a dynamic co-attention network for Q&A. It has a document encoder. I mean, no need to go too depth, but I'm just taking as an example that these kind of architectures have been used, but almost they are similar. Question encoder, document encoder, I feed into that, I form a similarity matrix or affinity matrix, whatever you call it, the same thing, and then I get the co-attention of it. So you will get to know what is co-attention. Okay. So if you see here, it looks very complex, but let me make it simple. There is a query, there is a document. On that query, I get a AQ is a attention similarity matrix or attention um, affinity matrix, whatever you call it, it's the same thing. So these matrices are based on the words which has the highest probability. I form a similarity matrix. That similarity matrix is again multiplied with the document, okay, and we get a concatenation. Basically, we concatenate both, and then we feed into the another CD is a document which is a summary of those two. Okay, so we get a summary
Summary of paragraph and question.
Yes. So that summary is formed based on the attention matrix and the document. So the CQ, if you see CQ, and I have sorry, AQ and AD. So AD is with Q, means attention of the document matrix is formed based on the rows of the queries, the questions, and AQ is attention query matrix is formed based on the columns of the document, right? So I form two different matrices, right? Those two matrices are feed into the CQ, which is a concatenation of that, and then I pass into that and I form a total, a matrix. Basically a vector and matrix calculation of these concatenation.
Okay. These two matrices are the same or the different?
Which two? They are different. They are different because one is from document. The attention matrix is based on the document and the query. Another is the query and the
Question.
yes. Question and the yes. Question and the
this. Okay. Now the question is now. One is coming from a document, right?
Yeah.
One is coming from a question.
Yes.
Where are you going to put the weights?
So weights, we with any network, we actually pass in the weights from the on the equation. Okay. So any equation we have y is equal to mx plus c. We'll always have the weight fitted, right? So it is now how you make it non-linear and linear. From that it changes the weights, right? Okay. So after that I apply bidirectional STM and I get the output. So just to understand co-attention, where the co-attention is actually playing picture here. You get that? So a CD, right? CD, I get a attention from perspective of document and the question, and a perspective of question through the document. So I have attention from both the sides. That's what the co-attention is. That is forming a matrix, and I'm feeding into the network.
That is AD and concatenate this with that.
Yes, correct. Okay. I'll go ahead faster. So co-attention layer again provides a two-way attention between the context and the question. However, co-attention involves a second level attention computation attending over representation that are themselves attention outputs. We use C2Q attention distribution AI to take weighted sums of Q to C attention outputs Bj. This gives us second level attention outputs of SI. Okay, is a mathematical formation. So if you see co-attention results in squad competition, so with F1 score and exact match score, and if you see here, so with test 80.4 is for DCI, dynamic co-attention network. Okay, that performs very well. See here. Okay, I'm not gonna just have a look. I'll go ahead with the next one.
Where is the 84?
What is the training data they use for this? Getting this out?
Squad competition, right?
So how do we evaluate?
See, one is F1 score. You know about F1 score, right?
No.
What is that?
Harmonic mean of precision and recall.
Precision into recall divided by precision plus recall. How does precision comes? dp by dp plus fn, and recall is dp by dp plus f. False negative, right?
Recall is
negative. False.
sensitivity.
Yeah. So for you see the matrix, right?
Confusion
confusion
matrix.
matrix. So for precision, it is always PP plus false positive. So
So basically, a harmonic mean.
recall is
Basically, a harmonic mean of precision and recall.
yeah. I mean that is not understandable by all the people, I think. But yeah, harmonic mean mathematical term it is. So shall I go ahead? Okay. I'm skipping this fusion net. Right. So another thing is with the L1 BERT preview. So we are using BERT here. So the transformer architecture used in BERT is sort of attention on derivatives more later. So if you see here, input is fed to the output network. So normally with BERT architecture also it is the same thing that we apply attention, and I'm not going in detail. I mean this is the last slide that I took. So but both are performing very well, L1 and BERT. Okay. So you see the spot leaderboard. Albert, so which is basically an ensemble model, that performed 89.731 with exact match. F1 score is very high, 92.215, which is very good, right? So this is recently in September 18, 2019. So probably an Albert single model performed 90.902, which is
What is EM or what is EM?
sorry.
What is EM? Evaluation matrix. Evaluation.
Yeah. Exact match. Exact match.
Okay, F1.
F1, I just not told F1 score.
Score.
When you say Albert ensemble model means it's ensembling multiple models of this kind.
Correct.
Yes. So this Albert we can use for multiple purpose, multiple. What are the cases? NLP translation.
Albert is an advanced version of BERT. So with high efficiency, and it uses less. I mean, the model is built for basically for training in mobiles or less exhaustive applications or systems.
Okay,
So
you can use it for embedded device.
efficiency is higher. Yeah.
Transform or something.
Correct. I did not. I mean, I cannot even cover Albert here. It's another research paper and it's a different topic.
See, you have an exact value of 86%. Then how F1 is higher than 86? Because when you say exact match, how
So
score will be higher?
exact match is I mean I'm exactly not sure that how exact match is done. Exact match is exact match. So exact match is something. It matches the complete the question that you are. So it's not a complex.
I understood that, but how can F1 be higher than exact match? That's my question. Because the score has to be.
I'm not sure.
So I think what they are saying is with the exact match algorithm, it is 86% correct.
Yes.
If it is F1 match, it is 89% correct.
Not F1 match, it's
F1
F1
match.
F1 is a score.
F1 is a score.
F1 is always a score.
So to achieve F1 score,
My question
89%
is, my
of
question
it,
is,
89.5% of the sample were able to do it.
We're talking about
For
exact
this,
match.
this is
EM.
86%.
Is it the same as accuracy?
See, I'm not sure
So
about
when you
EM.
say that exact match is 86%, that means your misclassification is 14%, 1 minus 86.
Yes.
This is the best result that it is getting.
True positive and true negative.
See, there may be some mathematical formula for calculating that.
So that's
I see normally with the exact match I did not I did not explore that how they have compared both EM and F1.
I'm not even asking the mathematics. I'm only asking a very basic question. Saying that when you say exact match, does it mean your correct classification? That is my simple question. Yes or no?
Correct?
Correct classification.
Yeah, but see, we actually compare, right? We compare with classifier.
Therefore, your exact match is nothing but your accuracy.
I mean, this is all are showing the accuracy only,
Okay.
right? What is the score? I mean, for any neural model, we find the score to get the accuracy, not the loss function, unless or it is if it is a what is it? XGBoost or machine learning.
It's not just accuracy matrix.
Yes.
A different kind of accuracy matrix.
Correct. Okay. I'll close it. End it. So next is so future scope with Q&A. So accuracy, how can we make MRQA right? Representative QA system more accurate? predictability. How can systems provide rationals for their predictions? Speed and scalability is still a area where we have to work on. How can systems scale to consider large context from long documents to whole web? Robustness is also one of the areas we need to focus. How can systems generalize to other data sets and settings beyond the training distribution? Data set creation, what are the effective methods for building new MRQA data sets? Apart from Squad, we do not have really a very good data set still. And data set analysis, what challenges do current MRQA data set poses? And error analysis, what types of questions or documents are particularly challenging for existing systems? So we need to explore these many things yet after this.
So this Albert is not solving this problem.
Probably few of them, but these are very hard to say because this again poses a question of summary or survey around particular things.
Can I use QA systems to do fraud analytics, fraud text analytics? Can I do that?
In fact, basically, these models will be very good because come back to the point that was there in the earlier slide. You showed those metrics, right? What I was thinking was you had two things on the. That's okay, I don't need it. You have two columns in the last. One is your exact match, and the other is your F1 score. Now, what it is telling me is if your F1 score is more than your exact match, okay, that means that the sensitivity is really high. So when he's talking about fraud, obviously it will be a great fit. Because if your F1 is more than your basic classification, that means your sensitivity is remarkable. Those are like very, very sophisticated models. You're training them so much, right? Unidirectional, then bidirectional, so many bidirectional layers. Obviously, your output will be that much more sensitive to capturing true positives.
All right. Thank you, everyone. I hope I'm able to make it more.
Push you there.